Hello, my name is Dr. Jacque Kelly, and I'll be presenting a brief look at the results of a combined electrical resistivity and ground penetrating radar study that my colleagues, Dr. Kelly Vance and Dr. James Reichert and I have been working on to better understand the shallow subsurface of St. Catherine's Island, Georgia, which is one of Georgia's barrier islands. St. Catherine's Island is located along the Atlantic coastal plain. The island's clastic surficial aquifer is susceptible to numerous saltwater intrusion events, which have been documented by Dr. Reichert. I refer you to his talk titled Saltwater Intrusion and Structural Controls Within the Groundwater System on St. Catherine's Island, Georgia, for a broad overview of the hydrogeologic background and for specific evidence of saltwater intrusion on the island. This LiDAR map on the left shows the location of our network of 18 well sites in the surficial aquifer. These wells range in depth from 20 to about 45 feet deep and are aligned along 3 transects spanning the width of the island from the marsh side to the ocean side. The field photo shows a typical well location. We try to give inclusive research experiences, so we have a few professors, some undergraduate students, some graduate students, and a few citizen scientists helping us out. The LiDAR map on the left also shows a linear alignment of freshwater ponds and wetlands, demarcated by the dashed line. Written accounts from the colonial period indicate that these water bodies had once been fed by artesian springs. As Dr. Reichert indicates in his presentation, these water bodies were likely created by collapse features in the artesian Floridan aquifer system and are water flow pathways that connect the surficial and Floridan aquifer systems. I mention these features because they demonstrate the existence of preferential water flow paths on the island and the need for investigation of these and other preferential flow paths to better understand current and potential future saltwater intrusion pathways. Dr. Reichert's well monitoring efforts indicated pronounced salinity spikes in data from several wells on the island. Of note here is that wells with salinity spikes were not consistently on the marsh side or the ocean side of the island, suggesting that there may be multiple methods of preferential groundwater flow. We therefore recognize that the subsurface and stratigraphic database for the island is insufficient to accurately understand the island's complex shallow groundwater system. These wells, along with a few other locations of interest, are circled on this LiDAR image. We targeted these locations for geophysical investigation, and they will be the focus of my presentation today. The overarching goal then was to use geophysical tools to investigate the structure of the shallow subsurface of St. Catherine's Island. Electrical resistivity tomography, or ERT, is a non-invasive way to image the subsurface. Our system is a multi-channel supersting system manufactured by Advanced Geosciences Incorporated. Our cable has 56 nodes that are spaced up to 3 meters apart, giving us the ability to image the subsurface down to a depth of about 40 meters. This field photo shows a crew of undergraduate students securing the nodes to the ground in preparation for data collection. A field crew of 6 can deploy and secure the cable as well as perform pre-data collection checks in about an hour. There are various array designs to send and receive electrical current from the cable. We used a dipole-dipole configuration, which is the most widely used array to collect ERT data. It typically took about 2 hours for the equipment to collect the data and then about an hour to disconnect the cable and pack up. We therefore were able to collect 2 profiles a day, so this is a relatively time-consuming task and really necessitates having target locations to image. ERT is particularly useful for providing information about bulk resistivity of the subsurface, including fresh and saltwater saturated sediments. Ground penetrating radar, or GPR, is also a non-invasive technique to image the shallow subsurface. Our GPR can be pulled behind a gator, as in this field photo of undergraduates collecting data, or it can be used on a push cart. We can image the subsurface down to about 20 meters. However, the GPR signal is attenuated by fresh water, so we start to lose the GPR signal at the top of the surficial aquifer. Taken together, GPR and ERT are complementary and work extremely well in our field setting because GPR identifies subsurface materials from the ground surface down to the top of the surficial aquifer. The ERT is excellent for giving us information about the thickness of the surficial aquifer as well as information about what is below the water table. I will be presenting some core data today that was collected by Dr. Vance along with a large number of undergraduate students. We collected core data using a tractor-mounted geoprobe rig that is shown in the picture on the left. The core data were cataloged by undergraduate students and by Dr. Vance. The initial cataloging in the field is shown in this field photo on the right. I will mention that this rig is also what we used to install many of our wells on the island. In the next couple of slides, I'll be presenting a series of images that show the subsurface of the island. The images will have GPR data, ERT data, and core data. Since the focus of my fieldwork was the ERT component, I will focus my presentation on the ERT data while highlighting a few key things in the GPR and core data. I will be presenting ERT data in the unit of ohm meters. Electrical resistivity is inverse conductivity. So as water content increases, the ERT signal decreases for a given bulk material. Therefore, saturated sand will have a lower resistivity than unsaturated sand, as shown in my simplification of ERT values, with saturated sand in green and unsaturated sand in yellow. Sand saturated with salt water would have lower values still. Another good general rule of thumb to keep in mind as we visit the data is that larger grain sizes should cause an increase in resistivity. For example, the ohm meters increase as we go from clay to sand and then to gravel. This slide shows the data for site S3. The GPR data are shown in black and white with GPR distance along the primary X and depth along the Y-axis. Earth surface is therefore across the top of the diagram. Superimposed on the black and white GPR is the ERT data in color with ERT distance along the secondary X. In all of these images, red hues indicate higher resistivity and blue hues indicate lower resistivity. Please note that the resistivity scales on the following slides will change and are maximized to show the full range of the data. The slides also show a very generalized description of the core data along the right side. Additionally, I have included the approximate locations of wells at each of the sites, as well as well depths and water level data that was collected close to the time of ERT data collection. In all the sites that I will show you today, we have a nested well set with one shallower surficial aquifer well and one deeper surficial aquifer well. Now that I have explained the layout of these slides, I'm going to talk about the data specifically at site S3. The core data from this site along the right of the diagram shows that the subsurface is dominated by sands to about 9 meters depth. Then there is a roughly 1 meter thick layer of sand with trace muds, followed by a roughly 1 meter thick layer of mostly mud and trace sand. At about 13 meters, the subsurface materials return to sand dominated. In the GPR data, there is attenuation of the GPR signal. In the most basic sense, attenuation in the GPR signal is shown by image blurring. Attenuation indicates the presence of water, which matches the well head data for the set of wells we have installed at this location. For the ERT data, the nearly vertical blue feature near ERT distance 52 meters suggests a connection between the shallower surficial aquifer and the deeper surficial aquifer. And indeed, we find that the groundwater chemistry of the shallow surficial aquifer well and the deeper surficial aquifer well at this location is nearly identical. I do interpret this ERT data more cautiously than the data from the other sites because it took 7 iterations for the inversion to converge on this model. and the root mean square error of this model is rather large for my liking. This slide shows the data for site N5 along the northern transect. The core data from this site shows that the subsurface is dominated by sand to about 9 meters depth, and then there's a roughly 1.5 meter thick clay layer followed by a roughly 1 meter thick layer of sandy mud and muddy sand, followed by a shelly mud layer. The GPR data shows a strong basal reflector at the top of the clay layer, which is dominated by low resistivity values in the ERT data shown by the blue hues. At our well site near ER distance 20 meters, the ERT data hover around 130 ohm meters, which can be consistent with sand with enhanced porosity as well as wet sand, compared to the red hues of higher resistivity at the same depth across the rest of the profile. The water in the deeper surficial aquifer well at this site has roughly twice the specific conductivity as water in the shallow surficial aquifer well. The shell-rich layer in the deeper surficial well is screened in also makes the water in the deeper well rich in calcium and carbonate. The statistics on the convergence of this ERT model are good. It took 4 iterations for the model to converge, and the root mean square error is relatively low. The last site that I will focus on today is site S4 along the southern transect. The data for this site was collected and processed by undergraduate student Ryan Dietrich as part of his senior thesis project. The core data from this site shows that the subsurface is dominated by sands to about 7 meters depth, where there is a transition to a sandy mud and muddy sand layer. Ryan has identified a number of fractures or faults in the GPR data at this site, which are shown by the vertical to nearly vertical red lines on this diagram. The well at this site has high chlorine and suggests that seawater is intruding laterally into this location via the fractures and faults. Furthermore, this well shows strong chlorine spikes following hurricane events. We have a deeper well at this site, which is not shown on this diagram because this data was produced by undergraduate students prior to installation of the deeper well. However, the deeper well we find has high calcium and low chlorine. The water chemistry of the deeper well precludes it from being a source of water for the shallower aquifer. Interestingly, the water chemistry in the deeper well falls along a mixing line between lower fluoride wells and seawater. The ERT data suggests a shallowing of the sandy mud and muddy sand layer to the west of this well site. I will note that Ryan has the east of the well site on the left side of the diagram and west of the well site on the east side of this diagram. And so the shallowing of the sandy mud layer is shown by this yellow hue across the diagram. The statistics on the ERT model are excellent and indicate that the model is a solid result. In conclusion, we have found a number of methods by which water is moving underneath St. Catherine's Island. At site S3, in orange here, we have evidence for communication between the shallow and deeper superficial aquifers. We may have evidence for enhanced porosity or some other conduit that is promoting saturated conditions at site N5 in blue. We also have evidence for seawater intrusion at site S4 in yellow. This site is not close to the boundary of the island, especially compared to some of our other well sites. But the site is near a series of freshwater ponds that are aligned, that were discussed in more detail in Dr. Reichert's presentation. Finally, we have evidence for a sag structure at site M6, shown in green here. Much more detailed presentation of the sag structure is given by Dr. Reichert in his presentation. Taken together, we hypothesize that the structural features promoting saltwater intrusion on the island are more common along the Georgia coast than previously recognized. Therefore, the ideas and methods presented here are likely applicable to the broader scale region's coastal geology. I now take this opportunity to acknowledge our funding agency, Georgia Sea Grant, as well as the St. Catherine's Island Foundation for supplying ferry transportation, on-island transportation, and cabins. Finally, the data presented here would not have been made possible without the volunteer efforts of about 15 outstanding undergraduate students. I thank you for your time and I hope you enjoyed my presentation.